Welcome to Microlecture 44, where we will talk about a specific type of E1 reaction, and that is the reaction of alcohols with strong acid H2SO4 as a catalyst. Just as before, when we covered a few SN1 reactions, and we talked about their mechanism, the reaction rate, and how level of substitution can affect the reaction, we're going to go through those same ideas with a E1 reaction. So let's just jot down a few reactions and keep careful track of stereochemistry in the products. So let's say that we start with this alcohol and we're reacting with H2SO4. This is a concentrated strong acid, and it's not any kind of reagent that we've encountered so far. So this is going to be a special case, and when we see the alcohol and the concentrated H2SO4, we're always going to think E1 reaction. That's how this reaction is going to proceed. So we would find all of the beta protons, beta to the leaving group, which we now know would be a water leaving group from the alcohol. And I have a couple of beta protons here, and actually I intended this to be a methyl group. So we have actually some beta protons here as well. And so there's a number of ways we can form product here, in two places that we could form a double bond. So we could form the double bond here, and that's actually the same thing as if we had formed the double bond there. And the other place where we could have ended up with a double bond is right here. Okay, so just depending on the beta proton that was picked in the mechanism. And the goal is always going to be, as we saw before with elimination reactions, is to form the most stable alkene possible if you can. And so this being tri-substituted is going to be our major organic product. The di-substituted possibility isn't going to get us to something as stable. Another example might look something like this. Right, so what forms when we react this alcohol with concentrated H2SO4? Knowing the reagents, and that's a red flag for E1 reactivity, I would go in and label any beta protons, and that's it for beta protons. There's nothing on the other side. So the possibility for products then would be this. We see that there's a possibility of forming the other stereochemistry. So cis, if you will, instead of trans, or Z instead of E. But having the highest priority groups as far away from each other as possible is more favorable, and so this is going to be our major organic product. So one more example. Let's do an example with the cyclohexane. It's got a stereocenter in there already, and then one stereocenter that's going to be the site of my reaction. And we're reacting concentrated H2SO4, so I know it's E1, so immediately I draw in any beta protons. And with regard to the last structure, we have, so this is actually the E, but we also could form the Z stereoisomer of that as well. But since it's not a major product. We won't bother to draw it out. Okay, so just like before, we could take one of these reactions and map out an energy diagram curve and think about how many steps there are, what's the rate limiting step, think about how fast are these steps relative to one another, and where do the intermediates turn up on the energy diagram curve. So let's take this reaction for an example, and we'll draw out the mechanism so that we can then draw out the energy diagram. All right, and so the first step in this mechanism is going to be to activate this poor leaving group OH with H2SO4. When you see H2SO4, you can think of that as H+. And so we're going to pertonate our alcohol, generating an intermediate with a positive charge on oxygen. Now we have a good leaving group, and that whole entire water molecule can depart, stabilized by the polar solvent system, aqueous H2SO4, and so we can generate the carbocation. And then it's a matter of going in and finding beta protons, and this is the beta proton that leads to the major organic product. If we take our conjugate base from solution, which is HSO4 minus, we can abstract that beta proton, kick the electrons inward to form the carbon-carbon double bond, and that is the step that leads to the major product. So if we count arrows here, there's actually 3 steps, 2 intermediates, and 3 transition states. Let's take a look. So our starting energy correlates with this alcohol. Energy is going to rise up and then fall back down, and then it's going to go ahead and go way back up again. Okay, so a high energy transition state, it'll come back down to a carbocation intermediate, and then we have approach of the conjugate base, which ultimately leads to our alkene product. And so our first intermediate is this intermediate, and our second intermediate is the carbocation intermediate. We have transition state 1, transition state 2, and transition state 3. And we're able to see that the rate limiting step is the one associated with the highest activation energy, and that's going to correlate with the loss of the leaving group water in this case, to form a carbocation. So as usual, the largest activation energy belongs to the rate limiting step of carbocation formation.